Hello, and welcome to Differential Equations. This is Lecture 8, Numerical Methods. Last time, we talked about autonomous equations. A first-order ordinary differential equation is autonomous when the right-hand side only depends on f of y, only depends on y, when you've written it in this normal form. An autonomous equation has an equilibrium at those constants where the right-hand side vanishes. And we spent most of the class talking about how these equilibria can be stable or unstable. Stable equilibria, this is when nearby solutions get closer and closer to the equilibrium, and unstable is when nearby solutions get further and further away. This time, we want to talk about the numerical computation of solutions. Right. So you have a differential equation. You might or might not be able to solve it explicitly in the way of getting a formula for y. But in any case, you want to have a numerical solution. You want to actually compute, say on a computer, the solution to the differential equation. So we've seen something for this already when we talked about slope fields. Recall that the slope field of a first order equation dy by dt is f of y comma t. This consists of small segments on the plane where the segment at a point t comma y has slope f of y comma t. The graph of a solution to this differential equation would have tangent line at this point t comma y with slope given by this function f of y comma t. So the segments are good approximations to the graph. Thus, we can construct the graph of an approximate solution by putting together segments of the slope field. Of some fixed length yielding a piecewise linear right, or polygonal function. This is known as Euler's method, right? Named after the Swiss mathematician Leonhard Euler. Let's do an example. Right, suppose we're looking at the differential equation dy by dx is minus y over x. Right, we've considered this equation before. The solution curves are circles. X squared plus y squared equals some constant. And suppose we want to apply Euler's method with initial condition y of 0 equals 1. Okay, so let me try to draw what's going on. Okay, so let's give ourselves x and y axis. And here is the point 0, 1. The actual solution curve through that point would be a circle. So say something like that. Okay, but let's pretend that looks like a circle. How the Euler method works is we start at that point, right? And we look at the tangent, we look at tangent segment, we have some fixed length, and we just follow that tangent. Then at the point we ended, we look at the tangent segment and we follow that. Then we look at the tangent there and we follow that. Then the tangent there, we follow that, and so on. As we get further and further away, our approximate solution gets further and further away from the actual solution, and we end up with something sort of like that. Okay, so modulo my drawing ability, that's what this method looks like in practice. Let us write down this method in detail. Here's the Euler method. Let's write it down more analytically as opposed to geometrically. Start with an initial value problem. dy by dt is f of y comma t, and y of a is y naught. So we start with this initial value problem, some interval on which we're interested in constructing an approximate solution. So let's call that interval a comma b. And let's choose the number of steps n. So this would be like, how many segments do we want to use? So once we made those choices, then we let delta t, this would be our step size, be b minus a divided by n. So we're just dividing the interval into n pieces of size delta t. And then we define t sub I to be a plus I times delta t, right? So these are our t coordinates of the segments we're looking for. We then define y sub I by the following iteration, right? So we already have y0 from the initial condition. So we define yi plus 1 to be yi plus f of yi ti times delta t, right? So we're just following the segment that goes through this point with slope f of yi ti. The solution to the initial value problem at position ti is approximately given by y sub I, right? So we write y of ti approximately y sub I plus, and so here's our error, big O of delta t, right? So the big O notation means an error of order delta t, right? So what that means is that for delta t small, this error is bounded above by some constant times delta t. So the order is just telling you how quickly something grows, right? So this says the error grows at most at speed delta t. Let's do an example. Consider the initial value problem. dy by dt is equal to t minus y. Y of 0 is equal to 1. Okay. Let us apply Euler's method. On the interval 0, 2, using n equal to 8 steps. Okay, so since we're using 8 steps, our step size is delta t be 2 minus 0 divided by 8, which is 1/4, right, or 0.25. That means that we're going to have T0 is 0, T1 is 1/4, T2 is 1/2, T3 is 3/4, and so on until T8 is finally equal to 2. Right? So, okay, to do Euler's method, we start out with y naught, given by our initial condition, right? So it's just this constant 1. And then yi plus 1 is going to be yi plus f of yi comma ti times delta t. So in this case, that's y sub I plus, right, f of yi ti is just the right-hand side. So it would be ti minus yi. And then it gets multiplied by delta t. Delta t is just 1/4 in this case. And We can also specify Ti. So Ti is just I over 4. Okay, so here is our formula for the updated y, right? If you give me yi, then we plug it into this formula and we end up with yi plus 1. Okay, so let's do that. So y1 would be y0 plus 0 over 4 minus y0 times 1/4, right? So that would be 1 plus minus 1 times 1/4, so 3/4. Y2 would be y1 plus 1 over 4 minus y1 times 1/4, right? But y1 was 3/4, so that's 3/4 plus 1/4 minus 3/4 times 1/4. So that's 5 over 8, right? Or 0.625. Y3 would be y2 plus 2 over 4 minus y2 times 1/4, right? So this would be 5/8 plus 2/4 minus 5/8 times 1/4, right? Which is 19 over 32, right? Or roughly 0.594, right? And so on until finally we get to y8, which is roughly 1.2. Okay, in this case, the differential equation is simple enough. We can write down the exact solution. Right, the exact solution is y of t equals t minus 1 plus 2 e to the minus t. And if you plug in 2, we find that y of 2 is approximately 1.2707. Right, so the error is roughly 0.0707. Right? If we had used more steps, or rather, yeah, or equivalently smaller step size, if we had used n equal to 16 steps, we would have ended up with y16 approximately 1.2361. So an error of roughly 0.0346, i.e., basically half the error. With twice as many steps, right? So that is exactly what you would expect from having an error that's big O of delta t, right? We expect that if we double the number of steps, then we should get basically half of the error, okay? The Euler method, or the Euler scheme, is a first-order method because the error scales like the first power of the step size, right? So delta t raised to the 1. right? It is desirable to use a higher order method where the error scales like delta t to the k for some k greater than 1. Right? If it scales like delta t squared, we call it a second order method. Delta t cubed is a third order method, and so on. Right? So one reason why this is desirable is that then we require fewer steps to get within a desired error. For example, if we'd like an error of size, say at most 10 to the minus 6, then a first order method would require roughly and about 10 to the 6 steps, right? So 1,000,000 steps to get that accuracy. A second order method would require roughly 1,000 steps to get the same level of accuracy. And a sixth order method would require roughly 10 steps to get the same accuracy, right? So of course, nothing's free. Higher order methods take more work to carry out. Another reason to use higher order methods is that the computer has some round off error, and that imposes a bound on how small a step size can actually be. Right? How small a step size can actually be computed. So if we want a small error, we can't necessarily just take arbitrarily small steps. Just imagine trying to carry out Euler's method using a calculator, right? Your calculator only has so many digits of number you can type in, right? And if you were to decide, I'm going to take a step size really small so that my error is really small, well, maybe your calculator wouldn't notice the difference between your TIs. And so you wouldn't really be able to carry out Euler's method given the round off error on your calculator. Of course, your computer has a much better round off error. It can handle much longer strings of digits, but it still has some bound on how many digits it can handle. And so you can't just take arbitrarily small steps and use Euler's method to get an arbitrarily small error. So that's why you want to have higher order methods. So here is one that's known as the improved Euler method. Okay, so just as with the Euler method, we're going to start with an initial value problem. dy by dt is equal to f of y comma t. Y of a is y naught, right? An interval a comma b on which we seek an approximate solution. And we choose the number of steps. And then let delta t be b minus a divided by n, and t sub I equal to a plus I delta t. Okay, so just setup is the same as for the Euler method. Now we choose, or rather we start with the constant y naught. And then define yi iteratively as follows. So instead of what we did with the Euler method of just in one go computing yi, here we're going to start by computing a predictor, it's called, like in Euler's method. All right, so I'm going to call it yi plus 1 tilde, because it's not the yi plus 1 we're going to end up with. And it's just what Euler's method predicts for yi plus 1. All right, so you just take the slope at the point yi/ti, multiply it by the step size and add that to whatever you have. And this is your predicted value of yi plus 1. And then we use this to calculate a corrector, right? So this is where we're going to improve on Euler's method. Instead of keeping this yi plus 1 tilde, we take yi plus 1 to be yi plus. So what we're going to do is take the slope at the point yi ti, and then we would like to take the slope at the point yi plus 1 ti plus 1. But of course, we're computing yi plus 1, so we don't know what yi plus 1 is, so we take our predicted value, average those two, and multiply that by the step size. Okay, so this corrected Euler's method or improved Euler's method gives us a second order method. Right? So the actual value of the solution at the point ti is like yi, but with an error of order delta t squared. Okay, this is a capital O. This is how I write my capital O's because I don't want them to be confused with zeros, right? So it's a capital O of delta t squared. Okay, so you can think of Euler's method as approximating an integral using the left-hand rule, right? So if you think of your integral as being the limit of Riemann sums, right? Your Riemann sum, you have a rectangle where your base would be the step size, and then you have to pick a height. And the left-hand rule says for your height, pick the value of the function at the left endpoint of the subinterval that you're using, right? The improved Euler's method is then like approximating an integral using, instead of the left-hand rule, the trapezoidal rule, right? So instead of picking the left endpoint and thinking of it as our rectangle as having a fixed height, here what we're doing is constructing a little trapezoid using the left and right endpoints of the interval, right? There are more sophisticated ways of approximating an integral. Another way of approximating an integral is known as Simpson's rule. And the corresponding numerical method for differential equations is the following, right? So this is known as the Runge-Kutta method, right? Named after two German mathematicians, Karl Runge and Wilhelm Kutta, who came up with this method around 1900. So what you do is you start, so it's going to start just like with Euler's method. Start with an initial value problem. Right? dy by dt is f of yt. Y of a is y naught. Right? An interval AB on which we seek an approximate solution and choose the number of steps and then you let delta t be b minus a divided by n, and define ti be a plus I times delta t. Okay, so we start with the constant y naught, and then define yi iteratively as follows. Yi plus 1 is yi plus, and then it's going to be, just like in the improved Euler method, we're going to take an average of slopes. Here, it's a weighted average. Okay, and the slopes we're using in this average are as follows. So K1 would be just like in Euler's method. But then K2 is f of yi plus K1 over 2. Advance Ti by step size over 2. K3, you advance yi by K2 over 2, and Ti is evaluated at the same point as for K2. And finally, K4 is f of yi plus K3, Ti plus delta t. Okay, so you pick these for slopes, and you take this weighted average of them, and that's how you update yi plus 1. This is a fourth order method. Y of Ti is yi plus an error of size delta t to the fourth. And this is a very popular algorithm because it gives you really good results, right? Your error is fourth order, and with little trade-off in terms of the computational complexity. So this gets used a lot. It's sometimes denoted RK4 because it's fourth order, and there are variations of this with different orders. RK2 is sometimes used to denote the improved Euler's method. Okay, we'll stop there and pick it up next time.